Okay, so we're doing double integrals over regions that are not rectangles in 15.2. And basically there's going to be two scenarios. So I think they call them type 1 and type 2. So there's something called a type 1 region. And then there's a type 2 region. I can not keep this straight in my mind. I don't care whether they're type 1 or type 2. What I like is the term vertically simple. Oops. Or horizontally simple. At least that tells me something geometric and not just an arbitrary labeling. Okay, so vertically simple means that a vertical slice will go from one curve to the other for all values of x over the region. So the idea is I'm going to draw two vertical boundaries, like this maybe, and have one curve on top, like that. Actually, I'm going to get rid of the vertical line on the right because it doesn't have to be like that. You can have them two curves come together at a point. Okay, so the idea is we do a vertical slice. I'm going to do a big fat green slice in the middle of this, like that. And okay, on the top, well, let me get some coordinates to all this. So first an axis for x and y. Okay, on the bottom, you'd have like one curve y equals f1 of x to y equals f2 of x. And then you'd have to have limits on x. So x would go from a to b, like that. And the region here is just R, as before. That's really bad. Not that it matters that much. And the idea is you're just going to do an integral over the green slice for a fixed value of x. So and this is basically how we define Fubini's theorem. So if you just integrate this function f of xy and just do it over a fixed value of x. So x is fixed, you let y vary, and for a fixed x, the lower limit for y would be f1 of that given x value, and the upper limit would be f2 of the given x value. So this is exactly how we define Fubini's theorem. We just say let the x value be fixed, figure out the range for y that goes with that x, and then do an integral. Then multiply by the thickness, which is dx, and add up again, where in this case x would go from a to b, like that. And then let me move this over a skosh, and I'm going to say that this whole thing is a double integral of f of xy dA over r. So that's for the vertically simple region. And it's called vertically simple because, again, the green vertical line that I drew, the top of it only touches one curve over the whole region. the bottom of it only touches one curve, a different curve, just one curve though, over the whole region. But that's a vertical line, so that's why we call it vertically simple. And of course, the horizontally simple, I think you know what that means. So these sort of, once you know what it means, vertically simple and horizontally simple, to me, just makes, it's just better language. Okay, so here I'll just do something similar. Like that. So you have two curves again. Okay, so this is your region R, and then this time you fix a Y value. And Y would go from one point to another like that. Sorry, X for that given Y, X ranges from one value to another. So on the right, say the small numbers are on the left. So you have to say on the left, X is like a G1 of Y. I don't have enough room. Oh, I should use G on all of this. Gosh, you guys, I'm sorry. See these F's that I put on the previous curve? I've already used F, so I'm not allowed to use it again. So forgive me while I do a little cleanup work here. I'm going to do a G1 for the lower limit and a G2 for the upper limit. The F is the integrand, so I don't want to reuse the letter F. And now, because I've used G for the vertically simple region, I guess I'll use an H for the horizontally simple region. Okay, I'm going to slide over here. Okay, so on the left, I'm going to have X equal H1 of Y on the left, and X equal H2 of Y on the right. Okay. And then we'll give limits on Y. So Y will go from C to D. Oops, sorry, I got those backwards. Lower limit will be C, upper limit will be D. Okay. And so this whole region is just R, if you like. I hate that. It's really bad. Okay, any questions about that? And of course, on this one, you're going to do your double integral, but you're going to integrate with respect to X first. So here, we'll write that the double integral over R of f of xy dA will be an iterated integral where we integrate f of xy. Now we're going to do dx first, which means we're going to hold y fixed. And for a fixed value of y, the lower limit on x is h1 of that y value, and the upper limit is h2 of that y value. We multiply by the thickness of the slice, which is now dy, and then let y vary from C to D and add up to all these slices, and we get the double integral. Okay, so that's what they call general regions, means you can do regions of just about any shape, and I would say you can't, unless you're willing, because not every region is vertically simple or horizontally simple. But I think it is safe to say that while regions aren't always one or the other, you can always cut them up. You can cut regions up so that you end up with a bunch of regions that are all either vertically simple or horizontally simple. You won't have to do anything like that, so don't panic. Okay, so what you need now are examples. So let me get my notes real quick. Looking for questions. Don't see any questions. Anytime you want to interrupt, you guys, you just shout out. Okay, so here comes one. So we're going to integrate double integral of 2x plus y squared dA over R, where R is the region bounded by y equals x, y equals x to the third, where x is greater than or equal to 0. Okay, so obviously you've got to be able to graph these, and then you can decide, well, how am I going to integrate it? Okay, so let's do a quick little graph. And I only have to do positive x here, because x is greater than or equal to 0. And then here's y equals x to the third. Okay. And up above is y equals x. This one's vertically and horizontally simple. That's nice. So you have options. You can look at it. You can think of it as limits that go from a bottom curve to a top curve. Vertical line touches the bottom, touches the top, and as you move the vertical line from left to right, it never changes curves. Okay. You can think of it as horizontally simple this way. So in this case, you draw a horizontal line and you think about how it moves from bottom to top. And always you have a left curve and a right curve, and the left endpoint of the slice always touches the left curve. The right endpoint always touches the right curve. Doesn't change, so again, it's horizontally simple. Okay, with the horizontal slice. It doesn't matter which way you view this, but in every, with the definitions here, I've got y as a function of x, so it makes sense, I think, probably to go vertically, since we've already solved for the vertical variable. Okay, so this is what I would do. So this double integral of 2x plus y squared, let's do dy, that's okay, we'll do it both ways. Dy then dx. Okay, so do bottom curve. To top curve for limits. So on the bottom, y is x to the third. And on the top, y is x. Okay. Just interrupt me if you have questions. Okay. And then of course, x goes from 0 to 1. Maybe that's clear, maybe it's not. The intersections of these two curves are at 0 and 1. So x is going from 0 to 1. That's all you have to do. Let's take a moment to evaluate it. Okay, so we're doing antiderivatives with respect to y right now. So 2x, y, 2x is a constant, so you're going to have a 2xy where y goes from x to the third to y equals x. and then plus y squared. But again, antiderivative with respect to y is 1/3 y to the third. And once more, y is x to the third on the bottom, and y is x on the top. So we'll do all that work, and then we'll integrate dx. I just want to pause, see if there's any questions. I don't see anything. Little algebra is going to be required here to clean up. So we've got this 2x, and then you can say, okay, there's a y that is x, and then minus a y that is x to the third. Okay. And then plus 1/3, and then there's a y that is x minus a y that is x to the third. Okay. Okay, pretty ugly. Let's keep going here. So integral 0 to 1, I see a 2x squared minus 2x to the fourth plus 1/3 x minus 1/3 x to the third dx. Okay, so that's bad. Don't see any questions. I feel like I made that really big. I'm gonna make it smaller. Yeah, that's better. And then keep going. Nothing that I can combine. Normally I'd combine terms. Can't do it. Okay, so here we have 2/3 x to the third from 0 to 1 minus 2/5 x to the fifth from 0 to 1 plus 1/6 x to the second, right, from 0 to 1 minus 1/3, oops, didn't take an integral, 1/12 x to the fourth from 0 to 1. Now putting in the zeros gets you nothing. In the end, it's just 2/3 minus 2/5, because everything's 1. The zeros vanish. Plus 1/6 minus 1/12. And I feel like there's a mistake. Okay, so it's this real tragedy here. Maybe you saw it. I'm supposed to do y to the third. So unfortunately, a lot of stuff has to go. I know this is frustrating, and I'm sorry, you guys, but there's a mistake. So we should have had, I'm supposed to be raising the y's to the third power here, which I didn't do. So y to the third, when y is x, that's an x to the third. And y to the third, when x is x to the third, is x to the third to the third, which is x to the ninth. That should be an x to the ninth there. And I apologize. Yep, there it is. Okay, so now I have to go through and do my cleanup work. So it's, the first part's right, and then I'm going to have a 1, that's a 4, so 1/12. That's an x, wait, hang on. So I get the 1/3 x to the third, minus 1/3 x to the ninth. There's a dx there. Now I think we can fix the next line, which will have a 1/12 x to the 4th minus 1/12. No, this will be 1/30 x to the 10th. And then both of those guys go from 0 to 1. And so this fixes as 2/3 minus 2/5 plus 1/12 minus 1/30. And I'm checking my answers now. This looks good. And it comes out to be 19/60. When you evaluate it. And I just did that on my calculator. Okay, and then I wanted to show how this could be set up as horizontally simple. Okay, so I want to go back and get this expression again and set it up differently. And I'm going to copy that picture down here again. Y equals x is fine. Y equals x to the 3rd is going to be changed to x equals cube root of y. Okay, y equals x is great. We'll leave that alone. What, or if it helps, we could say x is y. Same statement. Okay, but now we're treating this as horizontally simple. So I'm going to draw my horizontal line from left to right. Like that. Y is going to go from 0 to 1. But x is going to go from a curve to another curve. So when we set up this integral, we're still doing 2x plus y squared. But this time we're going to go dx and then dy. And on the left, we have to do curve to curve. But these are left and right curves. X is bigger on the right and smaller on the left. So on the left, x is y. And on the right, x is the cube root of y. Okay. Now, I see that cube root immediately. I don't want to do any more because I feel like this is going to be uglier. And these can look wildly different while you go through it, and they'll come out the same. So I still have y going from 0 to 1. Okay, and I know you guys can do this, but you're going to get fractional exponent because y, the cube root of y is y to the 1/3. And maybe I should have written that. But in the end, you're going to just get 19/60. Same answer. So it doesn't matter what order you do. It's just that some orders are easier than others. And I wrote 16, but it should have been 60. Same answer. Let's put the rules up real quick. Um, okay, so I'm wondering, are there any questions before we go on? Okay, so just real quick, these are things that you would expect, which are rules of linearity. And so when I say, so this goes under rules. Just to note, when I say f, I mean f of xy. When I say g, I mean g of xy. But it's just so much notation, it gets a little overbearing. So the first rule is a double integral over a region of f plus or minus, how about that, g dA is equal to double integral of f dA over r plus or minus double integral of g dA over r. So that's when you would guess, and you would be right. Second rule, you would also guess, and you would be right. Double integral of c times f dA. C is a constant. Okay, the constants come out. Again, that's what they call linearity in math. When scalars factor out and the operator is distributed across sums and differences, it's 1 and 2. So I would have a f dA here. Okay, so these are again called linearity rules. Let me do a picture for 3, and then the rule makes sense. So let's have a D1 and a D2. So I'm going to do it like this. Okay. This is R1, this is R2. And it's going to be given that the area of R1 intersect R2, it has to have 0 area for what I'm about to write. So the integral, the double integral, over R1 union R2 okay, of f, I can say of xy here, I don't mind, dA is equal to the double integral of R1 over f of xy dA plus the double integral of over R2 of f of x dy, xy dA. And again, that's yeah, under that assumption. Okay. Okay. You just split them up like that. And that's just another way of saying, okay, if you get a region that's not vertically simple or horizontally simple, cut it up. Cut it up, and you can make it into regions that are individually vertically and horizontally simple. Another thing is if you do, let's do 4, you just do a double integral of over a region R of just dA. That's 1. You're integrating 1, so double integral over R of 1 dA. So think of this as the volume under a curve of height 1 over a region R. And this has a constant height, so you can just do the base times the height. The base is the area of R, and the height is 1. So in the end, you just get the area of R. So you can compute areas with double integrals if you like. You don't have to. We've been doing areas lots of different ways in the past. So this is not an absolute, but every now and then you'll see this double integral of just dA and you know, oh, that's an area of a region. It's not really a volume anymore. It's just an area. Okay. So that's rule number 4. Rule number 5 says if f of xy is between two numbers, little m for min and big M for max. Okay, this is for all x, y, and m. Sorry, in R, x, y, in R. Then you can do this, that the double integral over R of f of x, y, dA. Well, you know that this is going to be between two volumes, okay? If you do big M, that's the biggest f gets times the area of R. That's got to be bigger because M is bigger than every value of f over R. And f is bigger than little m. So if you do little m times the area of R, that has to be smaller than the integral because little m is less than or equal to f. So this is just basically comparing 3 volumes and saying f has got to be in between these. Okay. Still got a few minutes left, and there's one more rule. So let's put down number 6 here. And it just says, maybe I'll just show you this. This is over rectangular regions only. And it's for a function of x times a function of y. Now this is actually from 14 point, is it 14? No, 15. So this rule is actually from 15.1. But I'm doing it here because I figured I'll just do all the rules together. So it just says this, the double integral over R, and let's not do it that way. Let's say, yeah, we could do it that way. Hang on. So let's have R be a rectangle. So R is like the interval from A to B on X cross the interval C to D on Y. Okay, so now I can say double integral over R of f of x times g of y. So a function of x times a function of y is the idea. And you can just do this. You can say it's the integral from A to B of f of x dx times the integral from C to D of f of y dy. So that's crazy. But it totally makes sense when you see the logic behind it. I mean, the logic is really simple. So just in parentheses, I'll add that in. So double integral f of x g of y dA over R is a double integral of f of x g of y I'll do dy first, it doesn't matter. Y goes from C to D, and then dx and x goes from A to B. Okay, and then you know that x is a constant, so f of x is a constant with respect to y. So you could rewrite this as an integral from A to B and bring the f of x outside of the first of the inner integral, like that. And then you'd have an integral from C to D of f of y dy. And then outside of that would be dx, like that. And then just say, oh, hang on a second. That this integral inside is a constant now because it's just in terms of y, and then you're evaluating at limits. That's a constant. So you can take that all the way out and just say, oh, well, then this is just an integral from A to B of f of x dx times the integral from C to D of f of y dy. So it's kind of crazy. Okay, so that's sort of a motivation for that. What time is it? 8:30. Let's see if we can squeeze one in. At least we can set one up, and then we'll stop. Let's do this real quick. Okay, so this one is a double integral over R of just y dA, where R is a triangle. It's the interior of the triangle, but I'll just say triangle with vertices 0, 0, 1, 1, and 4, 0. Like that. So really quick, let's graph it. Okay, so 0, 0, I'll put 1, 1 right there, and then 4, 0 will be way out there. Oops. Okay, let's connect these. Like that. So that's R. And we'll think of this as horizontally simple. I need curves on the left and the right. The left curve is easy. That's just x equals y. Okay. Or y equals x. Curve on the right is harder. I can do point slope form for this. The slope is, let's see, if I run 3, I have to rise -1. So the slope is -1/3. So you'd say y minus 0 equals -1/3 times x minus 4. I'm actually solving for x here. So I'd have -3y is x minus 4. So x is -3y plus 4 on the left. Sorry, on the right. Okay, so you always left curve to right curve if you're going to do horizontally simple, and this is definitely horizontally simple, not vertically. So let's just write down what the integral is and we'll call it a night. I'll send some reminders out about the review just so make sure you know exactly where it is. It's on the calendar if you look at that, but I'll put some reminders out in the email just to send it again. Okay, so double integral of y, we have to do dx first and then dy. X goes from left to right, left curve to right curve. So on the left, x is y. And on the right, x is negative 3y plus 4. Okay, and then y just goes from 0 to 1. Okay, that's it. And I'll let you guys evaluate that. Take care of yourself, everybody.